Welcome. In this video, we shall refer to the binomial theorem. In previous video, we learned the properties of binomial coefficients and presented the binomial theorem. We shall make use of this to deduce more meaningful facts and apply them to solve some problems. First, let us recall that the following are some of the key things that we covered in the previous video. We should remember them by heart. Let's now refer to the special case of the binomial theorem. It says that the sum of the terms n choose 0, n choose 1 times x, and so on until n choose n times x to the power n gives the value bracket 1 plus x to the power n. We can make use of this to get some formula on the sum of different binomial coefficients in some special pattern. And this may give meaningful interpretation in some practical problems. First of all, there are many nice relations and properties among the numbers in the Pascal triangle. In particular, would there be any pattern on the sum of all numbers in the same row? Remember the last time we noticed that the numbers in the Pascal's triangle are binomial coefficients. We wish to deduce that the sum of all binomial coefficients in the nth row of the Pascal's triangle gives the value 2 to the power n by making use of this theorem. In fact, this can be easily achieved by substituting x equals to 1 into the formula. Now, let's proceed. Here we would like to give a proof that the binomial coefficient is a positive integer. In previous video, when we first come across the definition of the binomial coefficient, we have already interpreted the meaning of the expression n choose r. It gives the number of ways of choosing r items out of n items when the order doesn't matter. Therefore, it is easy to understand that the binomial coefficient is a positive integer. If we do not think of this interpretation, we can still use mathematical induction to show that the binomial coefficient is a positive integer, although its formula is written as a fraction n factorial divided by r factorial times n minus r factorial. We can also refer to the Pascal's triangle so that during the whole proof it's more clear to see which number we have proved to be an integer and which numbers we haven't. Let us state again. We want to prove that the binomial coefficient n choose r is a positive integer, where n is any integer greater than or equal to 0, and r is any integer greater than or equal to 0 but less than or equal to n. So here, both n and r are changing. Let us denote Pn be the statement that the binomial coefficient n choose r is a positive integer, where r is an integer between 0 and n, and including these two endpoints. So we want to prove that this statement Pn is true for all n which is integer greater than or equal to 0. We can check those numbers at the top of the Pascal's triangle first. It is easy to check that the binomial coefficient 0 choose 0 is 1, 1 choose 0 is 1, 1 choose 1 is 1, by directly substituting the values of n and r into the formula n factorial over r factorial times n minus r factorial. In fact, we can also use the property that n choose 0 is always equal to n choose n, which is always equal to 1 for all n greater than or equal to 0. This property, which we have come across in last notes, can be easily verified by substituting r equals to 0 and r equals to 0 into this binomial coefficients formula. So it helps us also show that the value of 0 choose 0 is 1, 1 choose 0 is 1, and 1 choose 1 is 1 as well. This property helps us know that all the numbers at both edges of the Pascal triangles are positive integers. In particular, we have proved that the whole row of n equals to 0 and the whole row of n equals to 1 are formed by positive integers. That means P0 and P1 are true. Now for the induction hypothesis, let us assume that Pk is true, that is, the binomial coefficient k choose r is an integer when r is an integer between 0 and k and including these two endpoints 0 and k. This is the kth row here in the Pascal's triangle, and we assume that all of them are integers. Again, be aware that we have already proved that the statement is true for the row when n equals to 1. Now, we want to prove that the statement is true for n equals to k plus 1. That is, we want to show that the binomial coefficient k plus 1 choose r is a positive integer where r is any positive integer between 0 and k plus 1 and including these two endpoints. Previously, we already proved that all numbers at the edge of the Pascal's triangle are positive integers. In particular, it means that on the k plus 1th row, the first number, which is the binomial coefficient k plus 1 choose 0, and the last number, which is the binomial coefficient k plus 1 choose k plus 1, are positive integers. That means the statement p bracket k plus 1 is true when r is equal to 0 and r equals to k plus 1. Therefore, what's left are that we want to show that this statement is true for those r which is between 1 and k and including these two endpoints 1 and k. Now we make use of another property of the binomial coefficient, namely the binomial coefficient k plus 1 choose r is thus having the same value as the sum of these two binomial coefficients, namely k choose r and k choose r minus 1. This helps us know the value of a binomial coefficient in the k plus 1th row to be the sum of two other numbers in the kth row. It is very useful now, since we assumed that all numbers in the kth row are positive integers. So this property tells us that the binomial coefficient in the kth row will also be a positive integer, as it is formed by the sum of two integers on top of it. It follows that we succeeded to prove that if the statement is true for the kth row, that is, if the statement pk is true, then the statement pk plus 1 is also true. Therefore, all numbers in the k plus 1th row are positive integers. And since P1 is true, therefore this implies P2 is also true. And then P3 is also true. And so on.